All right. So today we're more than happy. We're excited to have Soham to tell us about a paper of Benny Yoshida and collaborators on chaos, complexity, and random matrices. Go ahead.
I'll be talking about chaos, complexity, and random matrices. That's based on this paper by Jordan Kotler, Nicholas Hunter-Jones, Junyo Liu, and Benny Yoshida. To get started, we'll talk about quantum chaos. Quantum chaos is not a very well defined, it's not a precisely defined concept, but it is understood as a general feature of strongly interacting systems. In recent research, quantum chaos has provided insight into quantum many-body physics and the quantum nature of black holes. In the study of black hole physics, in particular, the study of processes like scrambling and thermalization, it has been found that certain objects known as out-of-time ordered correlators, or OTOCs, can be used to probe the early time physics of chaotic quantum systems. And in 2016, a paper by Kotler and his collaborators showed that the late time physics of the SYK model can be captured using random matrix theory. Random matrix theory in was originally used to study resonances in nuclear physics, but since then it has been extended to various areas such as some research in string theory, large and quantum field theory, and it is generally understood that that chaotic systems have the spectral statistics of a random matrix ensemble. Um, in general, we can say that a random matrix theories can be used to describe the physics of chaotic systems.
Sorry,
So
I have a question, Soham.
yeah.
When you say small or large time,
Mhm.
compared to what?
Compared to the scrambling time.
Which is
We'll talk about that later on, but it's
okay.
scrambling time is generally understood to be the time scale at which 4.0 TOCs become small.
Okay.
Yeah. As we discussed, random matrix theories and OTOCs are both used to probe quantum chaos. As we stated and as we'll see later, the early time physics is captured by the OTOCs and the late time physics is captured by the spectral statistics of random matrix theory. So one of the aims of this paper, of this talk, um, is to find a sort of relation between the two concepts, between we'll find a quantitative relation between certain averages of OTOCs and the spectral statistics that come from random matrix theory. We'll also define a concept of K invariance, which helps us to define a time scale after which the physics of the theory can be captured entirely by random matrix theory. In addition to that, the decay of OTOCs with time is used to study processes such as scrambling and thermalization, and it is also used to quantify the degree of randomness or the approach to hard randomness of the system. So in this paper, we'll mostly be studying the Gaussian unitary ensemble. We'll compute its spectral form factors, and using that, we'll look at various concepts related to quantum information, such as frame potentials, quantum complexity, and approximate hard randomness. First, we'll define some generic concepts that will be widely used throughout. This object R2 here, that's called the 2-point spectral form factor, and that's defined as the average of mod z square, where z is the analytic continuation of the partition function. The average is taken over an ensemble of certain Hamiltonians, which appear here in the exponential. In standard random matrix theory ensembles, R2 has widely very broadly the following structure. So it starts off from a certain initial value. It decreases, reaches a minimum, then rises and attains a late time constant value. The period in which it is decreasing is called the slope. This minimum here is called the dip. The rise is called the ramp, and the late time constant value is known as the plateau. Uh, so yeah, let's discuss the Gaussian unitary ensemble. So the GUV is parameterized by three parameters: L, mu, and sigma. So the GUV is an ensemble of L cross L random Hermitian matrices. The off-diagonal elements of these matrices are complex normal mu sigma variables, and the diagonals are real normal mu sigma variables. So in mathematics, it's common practice to take L01, but it turns out that the eigenvalues will scale with the energy. So we choose the following normalization for the variance. We take L0 and 1 by root L. And in this case, it turns out that the eigenvalues don't scale with L. In the Gaussian unitary ensemble, the probability of a particular Hamiltonian h goes as the exponential of minus L by 2 trace of h squared. So here we can change the integration measure dh to d u dagger, and it's common practice to change the integration measure as given in equation 2. So c is some constant. Delta lambda is the van der Monde determinant, which is the product of the difference between the eigenvalues, and du is the Haar measure on the unitary group of size L. So
Sorry, Soham.
yeah.
In the previous slide, what did you mean by standard ensembles?
Standard ensembles, well, we can have things like Gaussian unitary ensemble, Gaussian orthogonal ensemble. We can have some things like symplectic ensembles. So that's essentially how the elements of the random matrices are distributed.
Yeah, so for all those ensembles, this general behavior holds.
Yeah.
Thanks.
Okay. Yeah.
Sorry,
so,
just one quick question.
Mhm.
So when you say the off diagonals are n mu sigma and the diagonals are n mu sigma r,
yeah.
you mean these are, you fix them? Well, not all of the off diagonals are independent, right? Like only the upper diagonal.
We can only specify the upper triangle, and the lower
upper
triangle
triangle,
will be fixed.
right? So that p of h e to minus l squared trace of h squared is the way. Okay, good.
Yeah, I mean, these are defined to be Hermitian. So
right.
Yeah. Okay, so yeah, so equation 3 defines a joint probability distribution for the L eigenvalues of these matrices, and that's given in this form. So exponential of minus L by 2 sum of the square of eigenvalues times the square of the van der Monde determinant. And in equation 4, rho lambda defines the probability density for a single eigenvalue. So that is just the joint probability distribution integrated over the other L minus 1 eigenvalues. And here we define a sort of simplified measure d lambda, in which we absorb all the other factors, and that allows us to define um, the ensemble average of a certain operator O. So O lambda, its ensemble average over the GUE, is defined to be integral of d lambda O lambda, where d lambda is the simplified measure. So certain other quantities.
Sorry, I don't quite understand. What was O lambda?
O lambda is a certain operator.
What is the lambda dependence of it?
Well, we could have an operator that depends on the eigenvalues, maybe the total energy or something.
Okay.
I mean, do you have any other intuition as to what sort of operators we might have?
Not really, no.
Okay. Yeah. Now we define this quantity rho n, which we call the spectral endpoint correlation function. So the rho n of lambda 1 to lambda n is defined like this. So the joint probability is integrated over the other L minus n eigenvalues. So in physical systems, we'll usually be working in the large L limit. And there are two standard results from random matrix theory. I don't know the proof of these two, but I'll just be stating them. So the first is Wigner's semicircle law, which states that in the limit L going to infinity, the probability density of a certain eigenvalue is given by this form. And the second is the form of the spectral 2-point function. So rho 2 as given in equation 6. So we see that in the L going to infinity limit, rho 2 has two terms. The first is a disconnected piece, which is the product of the individual probability densities, And the second is a sine squared kernel, which looks like this.
Sorry, the first line, equation 7.
Mhm.
This is rho lambda.
Yeah.
And the rho lambda is integral of d lambda 2 all the way to lambda n. So there is no L in there. So what you're sending to infinity is n, right?
I'm sorry, what's n again?
So rho
n
lambda.
as in 6.
Yeah, if I look at equation 6,
Mhm.
what you're dealing with,
I
L is
think
the,
the state.
I see. Sorry, I got your L and N mixed up. That's
I
right.
see.
That's
Okay.
right. Okay.
Mhm.
Good.
Yeah. So now we come to spectral
Sorry,
form.
can you go back one slide?
Mhm.
So equation 8 is the sine kernel for the
Yeah.
spectral
For
two-point
the
function.
2-point spectral, the spectral 2-point correlation function.
Do you have some sort of intuition as what this function is?
Some sort of, yeah. No, not really. I don't have an intuition what this might mean.
So the first term is, the rho lambda 1, rho lambda 2 says there are no correlation. Like this is the disconnected piece, right? The rest is normalization, right? And sorry, I'm a little bit confused. You've taken L to infinity, which means that that term is just 1, right? L squared over L times L minus 1.
You're right. This should be, this should
Is
be
that
going
an
to
exact result for all L? Maybe, I'm not quite sure. But anyway, as it's true that as L goes to infinity, so you just bring the rho lambda 1, rho lambda 2 to the left-hand side, and you talk about the connected piece. The connected piece.
This is the connected piece.
So now let's look at the connected piece. The connected piece is sine squared of L delta lambda over L pi delta lambda squared. So when delta lambda is very, very small, this is 1.
Yeah.
Right? Minus 1. Yeah, I guess minus 1. I'm a little bit confused about the sign, but anyway, when delta lambda is very small in units of L, this goes to 1. It doesn't need to be too small. It just has to be order
1 by L squared,
smaller than 1 over L, right? 1 over L squared or something.
Yeah.
Okay. Because the eigenvalue, sorry, go ahead.
Is the Wigner semicircle law true for all lambdas? Is that what you're saying?
Yeah, that's the implication. Yeah.
Okay.
So that would mean that when we increase the size of the matrix to some very large value, all the probability the probability distribution for all the eigenvalues becomes, well, it takes the same form. It has a lambda dependence, of course, but the L dependence drops out.
Sort of like
so is this for one instance of the matrix, or are you taking lambda 1 and taking an ensemble average over lambda 1?
Could you repeat your question? I didn't quite hear.
So is this an ensemble average over each eigenvalue, or are you looking at the eigenvalues of one instance of the matrix and then taking a distribution?
I think we are looking at each of them individually. I don't think we are taking an ensemble average or anything.
Sorry, this is the probability density for lambda.
Yeah.
Which lambda?
Yeah.
This should hold for any of the eigenvalues, I think.
Okay.
So we pick any of the L eigenvalues and its probability
there
density
there is one thing that what you can do is, if L is very large, the number of eigenvalues is very large.
Yeah.
So if you take one instance of the matrix, you can get a distribution of eigenvalues of that instance.
So what do you mean by that? Distribution of eigenvalues of that instance.
So take a large number of eigenvalues and plot the distribution of that. It is also taken from the same ensemble.
So wouldn't that just be a joint probability distribution?
So sometimes in random matrix theory, you assume that both of them are equal. The distribution of eigenvalues over one instance is equal to the ensemble average over many instances for each eigenvalues.
Okay, any other questions in this slide? Okay. So yeah, now we come to spectral form factors. So we had seen what spectral form factors are, and now we take the average of these over the GUE. So the 2-point spectral form factor, when averaged over the GUE, looks like this. So it's Z star, ensemble averaged over the GUE, which translates to this integral here. So at infinite temperature, that's beta equal to 0. We can find that the ensemble average value of the partition function z becomes L by t into J1 of 2t, J1 being the Bessel function of the first kind. And this function J1 of 2t by t, it's seen to decay as t to the minus 3 by 2 at late times. And generalizing the expression for R2 here, we can write an expression for R2k.
Sorry.
That's
Let's just try to understand equation 10, right? That's the result of a very concrete calculation. So this is you've taken beta equal 0.
yeah.
So that's your starting point is the Haar average.
Yeah.
Right? So E2 minus beta H is really the Haar average. And you take this guy and evolve it by e to the power of IHT. Yeah. And then you see a late time decay as 2 to the power of 3 over 2. So actually, one question. So this you have already taken the L going to infinity limits, right?
Yeah, we have.
Okay, yeah, good. I would be nice to understand this expression better, but yeah.
Yeah, I mean, in this paper, there are quite a lot of calculations, and yeah, it would be interesting to unpack each of them.
Sure.
Yeah. So at infinite temperature, we can write a generalized expression for R2k, which is just z star whole to the power k ensemble averaged over the GUE, which in its integral form looks like this, equation 11. So we can first deal with the beta equal to 0, the infinite temperature case. So there we have a contribution from coincident eigenvalues. So here when I equal to j, we can pull that contribution out and write L. And the other eigenvalues, the contribution looks something like this, L into L minus 1 times this average. And we have a row 2 inside the average. And since we are working in the large L limit, we can use the sine kernel form to split row 2 into the two parts that we had. So the two integrals evaluate respectively to j1 squared 2t by divided by t squared. And the sine kernel integral evaluates to this thing, 1 by L into 1 minus t by 2L times theta 2L minus t, where theta is the Heaviside step function.
Sorry, just one little question. If you go back to one slide back. Yeah, I'm just tempted to take equation 10 and take a bunch of integrals over this from minus infinity in t to plus infinity in t with some probability measure. It looks like it's real. It looks like something like you would do with recovery maps. But anyway, can you go to the next slide, please? Sorry, I got lost a little bit here. So, so the first one is again the Haar measure.
Which one?
12. Right, and then this R2 of t is.
So R2 of t we are evaluating starting from this thing, from equation 9.
I see. So yeah. It's a Haar measure for that.
Yeah.
Okay.
So
let's look
so
at
when
it.
we have I equal to j, we can pull that contribution out. That's essentially integral of d lambda times 1.
I see.
And the remaining part evaluates to the other thing. We have set beta equal to 0.
Right. So can you go to the next slide? Oh, okay, good.
Yeah.
So we get the step function. And what's the fall off of 13? 13 is 1 over t. Oh, wow.
All of 13. It's
Yeah.
it falls off as t to the minus 1 by t cube, I would expect.
Yeah, it's 1 over t cube, right? Oh yeah, it's a disconnected piece. I see.
Yeah.
All right. Okay, thanks.
Yeah. So putting together equations 13 and 14, we have the full expression for R2. So R2 looks like L plus L square R1 square minus L times R2, where R1 and R2 are the abbreviated forms of equation 13 and 14. R1 is J1 by T and R2 is this thing with the step function. So
sorry, I'm a little bit confused. So you have not taken L to infinity.
No, we are working in the larger limit because obtaining this J1 to T by T form required us to use the semicircle law.
Right, but if you look at equation 15, you have L squared terms, you have L terms, so you're doing some sort of perturbations here in 1 over L, or?
Okay, let's see.
I think you are doing that. So I think what's going on is probably that the disconnected piece of it has some trivial scaling that you do know, and you're only interested in the connected piece, which is 1 order lower. R1 of t was the coming from the disconnected piece, right?
Yeah.
Is that right? Yeah.
R1
okay.
is
So R2 of t is the, and plus 1, that plus L is the, I guess, the interesting part of this calculation, which shows a step function.
Okay, I see.
Okay.
I see what you mean. Yeah.
All right. Okay. Okay.
Yeah. Okay. So staring at equation 15, we can see that the plateau time is, which we denote by TP, is 2L, and the plateau value of the form factor is L, this constant piece here, and we can estimate the dip time using the asymptotic form of the Bessel function. So yeah, there's a slight problem here. So the dip time actually occurs at some intermediate finite time, but we use the asymptotic form of the Bessel function to estimate the minimum of R2. So using that, we find that the dip time is approximately root L, and the value of the form factor at the dip time also evaluates to something like root L.
Sorry.
Yeah.
You're saying that if I plot 15,
Mm-hmm.
I will see this slope dip.
Yeah, there's another subtlety here. So in the slope, there will be some sort of oscillation, which will correspond to the oscillations of the Bessel function.
Do you have the plot of this function? Is it somewhere in the paper, or?
Oh, this was in the paper. I think I should have included it, but it's not here.
No, that's fine. All right, that's
okay,
fine.
Maybe I can go back to this thing here. So I mean, here in the slope part, we have certain oscillations, and the dip is the minimum of the envelope of that oscillation.
But you were saying that this function that you just showed us captures all of these things. It has a slope with some sort of oscillation, whatever. There's a dip, there's a ramp, and then there's a plateau.
Yeah.
Okay.
Yeah. And the true minimum of R2 occurs at something like 1.18 times root L. But that can be seen from actual numerics. But since we are using a sort of approximation here, which is the asymptotic form of the Bessel function at finite times, we end up with a dip value something like root L. So this calculation can be extended to the finite temperature case as well, and in that case, sorry, were you asking something?
Yeah. So here you're gonna call square root L the dip time to be the scrambling time. Is that what you're gonna call, or?
No, I mean, we don't have a notion of scrambling yet. So this is just more related to approaching Haar randomness. Scrambling time will be somewhat different.
And so the plateau time, but here you're saying that the dip is at square root L.
Yeah.
And the plateau is at L. So the plot you were showing is sort of log for T, for T, right?
Which plot?
Yeah,
This
this
one?
one. Yeah, it
Yeah.
looks like, you know, yeah, that's a log plot. That's right.
Yeah.
Yeah, good. Yeah, yeah. Right, sure. Because it was like almost 100
yeah.
and then 10 to the power 4, right?
Yeah.
Yeah.
Okay. R2 can be evaluated at finite temperature as well. So in that case, the R2 looks much uglier. So it has this form. Analyzing it, we can find that the plateau time will still be 2L, and the initial value will be something like L square H1 square beta, where H1 is defined as J1 of 2I beta divided by I beta, and the R2 at the plateau time will be L times H1 of 2 beta. And again, we use the asymptotic form of the Bessel function and estimate the dip time and the value of the form factor at the dip time. And it turns out that it is root L times 1 plus some higher order terms in beta, the first order correction being at beta squared. So clearly, the smaller the value of beta is, the better our approximation is. And yeah, there's another thing. So at beta equal to 0, we hadn't seen the slope has certain oscillations corresponding to the Bessel function. But when we have non-zero beta, those oscillations smoothen out. So
Sorry, just one little comment. So here you have beta plus IT, right? So large time or small beta is all relative to the other parameter, right? So you're comparing T and beta.
here beta is to be, the analytic continuation of time is a temperature, right? So this should be understood as some large finite temperature,
Analytic
a small
continuation
beta.
of time is like Euclidean is tau that has periodicity beta, right?
Yeah.
I
So
think, yeah. All right.
uh,
Okay.
I'm sorry. What
That's all right. I'm just saying that the perturbation theory in beta and T could be swapped.
Okay. I see. Okay, and we can work out the 4-point spectral form factor as well, which has a pretty complicated expression. So just quoting the results here, the initial value is L to the 4. The dip time again turns out to be root L, and the value of R4 at the dip time turns out to be L. The plateau time is 2L, and the value of R4, the plateau value of R4 is 2L squared. So we have a general pattern for a 2K point spectral form factor. So it starts off from an initial value of L to the 2K. Then it decays as J1 to the 2K of 2T divided by T to the 2K. It reaches a dip value of approximately L to the K by 2 at a dip time of root L. And then in the ramp part, it grows as T to the K, and all of them have a plateau time of 2L and a plateau value of K into L to the K.
Sorry, all the odd ones are 0, vanish. Is that right? R3, R5.
Yeah, they should vanish. Yeah.
Sorry, why do they vanish?
So we would have something like Z star and Z that I think would become an odd function under the Haar integral.
Okay.
Roughly speaking, it's like the intuition is there's a Gaussian and all the odd point functions of it will go away.
I see. Thank you.
Okay. So now we discuss out of time ordered correlators, OTOCs.
Actually, can I ask another question? Can you go back to the last slide?
Yeah.
So here you're saying that Z2 R2K has, so I'm just trying to understand the dip value and the plateau value based on just like heuristics. So let's forget about K. So it scales like L to the power of K. Is there a way to see that? Probably there is a simple way to see it, that is L to the power of K over 2 and L to the power of K. But anyway, I don't see it either way. That's fine.
Actually, Keiichiro, coming back to your question, RK for odd K won't always be 0 because we had found that R1 is non-zero, right? we had found that the expectation value of Z in the Gaussian unitary ensemble is something like, where was it?
Yeah.
Yeah, we had found that it is something like J1 by T.
But the connected piece is the thing that vanishes.
Yeah.
I mean, the physics of it is really in the connected piece. The disconnected piece is probably all fixed by a weak rotation, weak contractions.
Yeah. Okay, so we'll discuss OTOCs now. So as we had stated, quantum chaos is also characterized using OTOCs, and we'll see how OTOCs are related to these spectral form factors. So we consider a system of n qubits, which is a 2 to the n dimensional Hilbert space, and we look at this 2-point function, which is called an autocorrelation function, A0 A dagger T, and A we pick to be a Haar unitary on the unitary group of size 2 to the n. So it turns out that this function defined here, when we compute the Haar integral, it turns out that integral dA of this 2-point function is trace of e to the minus iht squared divided by L squared, which is precisely R2H divided by L square. Now note here that R2, I mean, initially what we were denoting as R2 was an ensemble average, and here R2H is the value for a particular Hamiltonian, which is the Hamiltonian which is used to evolve the operator A in time. So this idea can be.
Sorry, I don't understand the statement. So what's the physics of this statement? So the integral of d of a, this is the 2-point function.
This is the 2-point function, and we find that
Time.
its Haar integral at infinite temperature can be related to the spectral form factor.
Okay.
I have a question. Is there any assumption about locality of the Hamiltonian for this evolution?
In this case, I mean, there might be assumptions about locality of the operator, but
Okay.
because I mean, if we start off with local operators, the 2-point function might initially be 0. But what do you mean by assuming locality of the Hamiltonian?
So the Hamiltonian can have interaction part, and it depends on like how the it depends on the locality of interactions, right? Like how far things can interact each other.
It's a quantum mechanical system, 0 plus 1 dimensional.
Okay.
So there's no spatial locality.
I see. Okay. Okay.
Yeah, so this idea can now be generalized to 2K point OTOCs, and we consider the following OTOCs: A10 B1T, and a string of such operators up to AK0 BK of T, and we pick the product of all these operators to be the identity. So performing this Haar integral, we find that the average value of this 2K point function evaluates to R2K of that particular Hamiltonian divided by L to the 2K. And so here we had picked a very specific relation between the A's and the B's. So we find that I mean, we can find that if we change the relation between the A and the B. So for example, if we define each BI to be the dagger of each AI, will still be satisfying this equation. We can end up with a different value. So the particular example that was discussed in the paper, it defined each BI to be the dagger of each AI, and we ended up with something like RK times RK. So square of RK divided by, I think, L to the 2K minus 1, something like that.
Is the product equal to identity at all times, or is it only
at that's at time equal to 0.
Okay, so
Yeah,
this is
because
only for
I mean
t equal to 0.
Yeah. So yeah, whenever there's no time label here, that would mean t equal to 0.
Sorry, this is this condition
Mhm.
says that B1 is A1 dagger, right?
Which condition?
In particular, BK is blah blah blah.
Oh,
That
k
says
is the last one.
oh, K is the last one. Oh, I'm
Yeah,
sorry.
it's not each index.
Yeah. Okay.
Yeah.
Sorry. Wait. No. These are unitaries or what?
Yeah, these are these are unitaries.
Unitary operators. Okay.
Yeah.
Good.
Yeah. Yeah, it turns out that spectral statistics, they ignore the spatial and the temporal locality of operators. So these the endpoint functions, the OTOCs, they are generally dominated by non-local operators. So that's how we say that the OTOCs and by extension the spectral statistics would ignore the spatial locality of operators. And it also turns out that the temporal locality of the operators is also ignored. That's because I mean, if we compute some non-out of time ordered correlators, such as there was again a specific example. We can pick some A1, B1, A2, B2 with A1 defined at time 0, B1 at time t, A2 at time 2t, and B2 at time t. So the result comes out to be equal to the OTOC. So that would indicate that the time ordering of the operators is also not respected by the spectral statistics. So the intuition for this is easy to see for the GUE, because by Haar invariance of the GUE, we can change the basis to anything we like, and that will cause the system to delocalize immediately. And so any temporal correlations are lost. In other ensembles, I don't really have an intuition as to what may be happening, but here
can
the
you
Haar invariance sort of gives an intuition for this.
can you repeat your intuition? I didn't get that. Can
Yeah.
you say it again?
So the intuition is, I mean, GUE has Haar invariance, and due to Haar invariance, we can change any operator A to something like UA U dagger at any time, even at time equal to 0. So any locality of time that may be there is immediately lost.
Okay.
Does that make sense? Or
I didn't quite understand, but it's all right. We can discuss
Sorry,
later.
what is the Haar invariance?
so Haar invariance here, I mean, the condition is more or less like, I mean, invariance under a unitary change of basis.
So it's unitarily invariant.
Yeah.
That's why it's called GUE.
Okay. So now we look at the averages of OTOCs over the Gaussian unitary ensemble. So we again pick this function A0BT averaged over the GUE. So it's defined to be integral dh A0BT, and due to the Haar invariance, we can insert the Haar measure U, and it takes the form given in equation 26. And after performing the Haar integral, we find out that the average value of the 2-point function is given as in equation 27. And it turns out that if A and B are not equal to each other, this function will go to 0, the average value. And if A and B are equal to each other, then it takes the value R2 minus 1 divided by L square minus 1.
Sorry, what is the integral over H?
Mhm.
What is the integral over H?
Integral over H is that's the Hamiltonian by which we are evolving. So there's a
But-
B of t, right?
Yeah, but you're integrating over all possible H.
Yeah.
I see.
So I mean, yeah, since this is an ensemble average, we would have to consider evolution by all possible Hamiltonians in the ensemble, right?
Yeah.
Yeah. So now we see that if A is equal, so if A is equal to B, we end up with this value for the 2-point function. And if R2 has a very large value, then we can write the following. So A0, a dagger of t averaged over the GUE becomes equal is approximately equal to R2 divided by L square. So we can do a similar analysis for a 2K point OTOC, and it turns out that the 2K point OTOC is given by this 2K point function, which is the 2K point correlation function at time 0 into R2K divided by L to the 2K. And yeah, this would be non-zero when the operators multiply to the identity, and when they don't, it can be shown that these OTOCs go to 0. And yeah, so these we had specifically chosen the correlators to be out of time ordered. So if we pick some random time ordering, so the ith operator is defined at a time ti, then it turns out that the average of that correlator over the GUE is the product of these guys, the trace of e to the minus I, the time difference between ti plus 1h. So this is this justifies our previous statement that even non out of time ordered correlators can give ensemble average values which are equal to the OTOC. So this sort of justifies our statement that temporal locality of operators in the GUE is ignored by the GUE.
The coefficient of equation 31 on the right hand side.
Yeah.
Do you have only A1 and AM, or do you have all the other operators AI as well?
Yeah, we have all the AI as well.
So it's not a two-point function that you've written.
Oh, I'm sorry. I'm sorry. There are all the operators are present here.
Okay,
that's a typo. Okay, so yeah, so now we discuss how how processes like thermalization and scrambling can be quantified by the time decay of these OTOCs. So first we discuss thermalization. So in black holes, thermalization is the loss of quantum information as seen by a local observer, and it is associated with the decay of 2-point correlation functions, which look like A0 and BT. So suppose A and B are local operators defined on two Hilbert spaces HA and HB, and since we are studying black holes, these two Hilbert spaces would correspond to the infalling and the outgoing Hawking radiation. So the 2-point correlation function is a measure of how much information about how much information about the radiation that has fallen into the black hole can be retrieved by collecting the information from the outgoing Hawking radiation. So as these correlation functions typically have small values, and this tells us that it's very difficult to retrieve a quantum state that has fallen into the black hole. And the fidelity of this reconstruction, it scales as the square of this 2-point correlator. So yeah, so now for the GUE. Sorry.
Yeah, I have a question. What is HA and HB specifically to the case of black hole? Yeah.
So here HA would so A is a certain quantum state that's falling into the black hole, and B is the quantum state that's coming out, the outgoing Hawking radiation. So those two Hilbert spaces are HA and HB.
Okay, thank you.
Yeah. So in the GUE, we had found that at early times, this correlation function is given by R2 by L squared, which is J1 of 2t squared divided by t squared. So this shows us that the time scale for thermalization in the GUE, which we denote by T2, is order of 1. Now we come to scrambling. So scrambling is the phenomenon of delocalization of quantum information. So in the context of black holes, we could have a certain tensor product state that's falling into the black hole. And once it has fallen into the black hole, the information can get stored in the form of correlations between these systems. And that's intuitively to be understood as the delocalization of the quantum information. So this phenomenon is known as scrambling, and it is probed by the decay of 4-point OTOCs. So we can consider a 4-point OTOC that looks like this. So A0 BT, A dagger 0, B dagger at T. So if B0 is initially a local operator, under time evolution it becomes non-local, and the OTOC here, it measures, it quantifies how non-locally BT has evolved. And the time scale for the decay of this 4-point correlator, which we denote by T4, is the scrambling time. So yeah. When the product of these 4 operators is identity, then we had found that this 4-point correlator ensemble averaged over the GUE is approximately equal to R4 by L to the 4. So since at early times we can write R4 is approximately R2 squared, we have the following relation. So the scrambling time, sorry, so this 4-point correlator looks something like J1 to the 4 divided by T to the 4. And that would show us that the time scale for scrambling is also O1. Now,
Can you go back to the last slide?
this one?
Yeah.
Yeah.
So you define the time scale for thermalization from the 2-point function,
Yeah.
and then you define the scrambling time from 4.0 talk.
Yeah.
And you said that in the random matrix model, they're the same order.
Yeah.
Yeah.
So
Thanks.
yeah, in this specific random matrix ensemble, the GU. So yeah, this result that the scrambling and thermalization times are at the same order of 1. This contrasts with many known results. So first of all, in large and CFTs with classical gravity duals, we have this result that the scrambling time is at a higher order of magnitude than the thermalization time. Also, the scrambling time being order of 1, it violates the conjecture that black holes are the fastest scramblers in nature, and it also violates the no cloning theorem of quantum mechanics. And it also turns out that in actual physical chaotic systems, non out of time ordered correlators would behave differently than OTOCs when averaged over the GUE. So it's not difficult to see why this is happening. That is because time evolution under the GUE would does not respect any notion of locality. So in actual chaotic systems, the space-time locality is lost after the scrambling time. So this leads us to believe that the random matrix theory, the GUE, it accurately describes the physics of chaotic systems at late times, which is times after the scrambling time scale. But at early times, it fails. So to study this phenomenon of when we can start using random matrix theory to study the physics of chaotic systems, we come to the concepts of K designs and frame potentials, and in a later section we'll quantify it better using the concept of K invariance. So in black hole physics, the internal dynamics are often modeled as evolution by Haar random unitaries, and the black hole states are often considered to be certain pure states that are generated by Haar unitaries. And now generating a Haar random unitary is it's impractical because it has exponentially increasing circuit complexity. So in practice, what we do is we consider what is the ensembles which are known as K designs. So K designs are ensembles which reproduce the first K moments of the Haar ensemble. So yeah. So yeah, we study time evolution by the GUE, and we look for the time frame after which it approaches Haar randomness. That is to say, we look at the time scale at which we can say that it forms a K design. Yeah. Yeah, we consider a finite dimensional Hilbert space and an ensemble of unitary operators that are acting on it. So taking an operator that's acting on the that belongs to the algebra of H tensor product at k times. We define this object phi epsilon k, and we call it the k-fold channel of O with respect to the ensemble E. So, oh, sorry, this E, not epsilon. Yeah. So this object phi is defined as the following integral, and we say that an ensemble epsilon is a unitary key design if and only if phi E is equal to phi over the Haar ensemble. So that would indicate that the first k moments of this guy are equal to the first k moments of the Haar ensemble. So an equivalent statement would be the 4-point OTOC is averaged over the ensemble E, and the 4-point OTOC is averaged over the Haar ensemble coincide. In that case, we can say that E is a K design. And yeah, now we define these objects which are known as frame potentials. Frame potential helps us to quantify how close an ensemble is to being Haar random. So the frame potential Fe is defined as follows. It's an integral over U and V, which belong to this ensemble. Trace of U dagger V to the power 2k. So in some sense, this can be shown to be a sort of a distance squared between the k-fold channel over the ensemble E and the k-fold channel over the Haar ensemble. And yeah, so for k that's less than or equal to L, the size of the GUE matrices, it can be shown that the frame potential for the Haar ensemble is k factorial. And for any given ensemble, the frame potential will be greater than or equal to the Haar value. So so this object Fe minus F Haar, it measures the closeness to Haar randomness. So yeah, now a couple of slides on computing the frame potentials. So the first frame potential, it evaluates to this object. These are for the GUE, by the way. So the first frame potential evaluates to R2 square plus L square minus 2RT divided by L square minus 1. So at early time this goes as L square, and near the dip time, that's root L, we observe that the frame potential reaches a value of 1, which is the Haar value. And at the dip time, it forms an approximate 1 design. At late times, the value of R2 is L, and the frame potential value is 2. So here we observe that we start off when we start off, it's obviously not a K design. At an intermediate time, which is around the dip time, it forms a 1 design, and at late times the frame potential is twice the Haar value. So we obtain a K design at certain intermediate times, and then we deviate from Haar randomness later on. So similarly, we can compute the other frame potentials. So we can compute F2. F2 at time 0 looks like R4 square by L to the 4. At late times, it reaches a value of 10. And again, interestingly, at the dip time, the F2 has a value of 2, which is again the Haar value. So it becomes a 2 design at this point. So we can obtain a generalized expression for the kth frame potential. So at initially it has a value of R2k squared divided by L to the 2k. At late times, it has a value of k factorial plus certain terms which are suppressed as 1 by L squared. And at the dip time, it obtains the Haar value of k factorial. So
Soham,
yeah.
So in K design, do you have any intuition as to what it means to put a cutoff in the moments?
Sorry?
So you're putting a cutoff in the moment, right? The
Yeah.
ensemble K design captures first K moments.
Yeah.
So is there any physical intuition? I can't. Not.
Physical intuition about the value of k?
Yeah. What does it mean to put a cutoff at small k, or what does it mean to put a cutoff at large k?
So we could say that if k is chosen to be large, then the ensemble is closer to being Haar random. What would it mean physically? Physically, it would probably mean, okay, no, sorry, wrong. Sorry, I don't have an intuition for this.
So far, to capture chaos, you needed only 4-point functions, right?
Yeah.
So how does it matter if you have higher moments or not? I mean, thermalization time is defined, I think, using 2-point functions.
Mm-hmm.
Scrambling time using 4-point functions. So why are we bothering about higher moments? I mean, yeah. So that was just a doubt. I think you
So
can continue.
one thing we could say is once we approach hard randomness after that point of time, the physics could be described entirely using the random matrix theory. So random matrix theory, as we have seen, it fails at early times. So if we could obtain a time scale at which this becomes approximately hard random, then we could say that from that time scale onwards, it's described entirely using random matrix theory. So so I'm guessing if we pick a larger k, it's closer to being hard random, and yeah, maybe we could say that we have an onset of random matrix theory instead of relying on OTOCs. But I'm guessing, I'm not really sure about the answer.
Okay, thanks.
Yeah. Yeah. So as we see here, near the dip time, the frame potential again is seen to oscillate. So this is F1 and this is F2. So the first time at which the frame potential reaches the minimum Haar value, that corresponds to the first zero of the Bessel function, and that's at t equal to 1.92. Okay, so before discussing K invariance, we'll briefly discuss quantum complexity. So the quantum complexity of a state is defined as the minimum number of local quantum gates that are needed to create the state, beginning from a product state. So it's used in study of topological phases of matter, and it has been considered in ADS CFT as a possible CFT observable to study the late time dynamics of ADS black holes. So we do have some intuition about quantum complexity growth at early times, but at late times, that's after the scrambling time, we don't have a very good idea for it. So the quantum complexity for an ensemble E that's acting on an n qubit system and is approximately a K design. It can be shown by certain counting arguments to be bounded below by this thing. So the complexity is bounded below by 2kn minus the log of the kth frame potential divided by 2 log n. So first we look at the bound for small values of k. So yeah, the the first dip time at which the frame potential reaches the minimum Haar value is order of 1. And at this time scale, we can write R2k as R1 to the 2k. So here the gate complexity is bounded below by this object. And we can write in big O notation, we can write the complexity is order of kn divided by log n. And at finite temperature, we can use the form of the Bessel function, which is t to the minus 3 by 2. And there we obtain that the complexity is has a log time dependence. So up to the dip time, the quantum complexity grows at least logarithmically in time. And for large k, we can again do a computation, bound the Bessel function, and we can observe that fk, we write k equal to cl, because all these notions of k designs and Haar randomness are only valid up to k being order of n. So we define k equal to cl, and we find that fcl is bounded by l to the 2k and e to the minus 2 ct squared. And we find that the quantum complexity is greater than or equal to ct squared divided by log n. And yeah, so this indicates that the complexity grows at least quadratically up to the dip time. So at this point, the paper mentions a connection to the ADS-CFT correspondence. So according to that, in ADS-CFT, the quantum complexity is related to the volume in the bulk, and so it initially grows quadratically and then it grows linearly in time. So I don't really know what that means. So Nima, could you say a few words on that?
It's a long story, but um, it's a pretty long story. It has to do with um, the growth of the volume. Actually, even the volume is not quite the right measure. So it's a long story. The story is like this: take the thermal field double, right, and evolve. Look at the RT surfaces that go from the left side to the right side.
Okay.
So this is like you have two boundaries, left and right boundaries, split each of them in half, right? There will be an RT side, or there will be some RT surface that goes in between the two. Now, this RT surface, as you evolve forward in time, the length of this RT surface, the area of it, just keeps increasing. The question was that what is a quantity, or yeah, the length of the wormhole is sort of like related to the length of the wormhole, right? The question was that what is the quantity that is proportional to that, and it was proposed as complexity. Then there was a fight about whether it's volume, whether it's the Wheeler-DeWitt action. It's a very, very long story, so we can skip that. Right? So it could be it could be a full other talk. All right, yeah.
Yeah, so this is the last few slides. Yeah. So now we come back to the concept of K invariance. So as we saw, random matrix theory fails to characterize chaos at early times, and that's because the GUV Hamiltonians are instantly delocalized due to their Haar invariance. But as we have seen, the random matrix theory can capture the late time behavior pretty well. So now we had seen how the frame potentials behave. We had seen that the frame potentials approach the Haar value at certain intermediate times, but then rise again. So they are not monotonically decreasing as we might like them to be. So in order to define such a quantity, that quantity is the K invariance. We start off with the Haar invariant extension E tilde of a certain ensemble E. So that's defined in this way. Yeah, it's defined in a sort of roundabout way, but yeah. So the essential feature is that once we define a Haar invariant extension for any ensemble, it is a K design. Its first K moments correspond to the first K moments of the Haar ensemble. And yeah, E is said to be K invariant if and only if we have that the K-fold operator over E equals the K-fold operator over E tilde. And the ensemble is said to be Haar invariant if and only if it is K invariant for all K greater than or equal to 1. So yeah. Using the Haar invariance of the GUV, we had seen that at late times the OTOCs are characterized by random matrix theory. And the time at which we achieve K invariance, that defines a time scale after which the 2K point OTOCs can be entirely characterized using the spectral statistics. So defining this operator S, which is the difference of an integral over an ensemble E and its Haar invariant extension, and using this inequality that trace of S dagger is greater than or equal to 0, we find that the frame potential for an ensemble is always greater than or equal to the frame potential for its Haar invariant extension, and equality occurs if and only if E is K invariant. So maybe we should yeah. So I should have included a graph here as well. So it turns out that unlike the frame potentials, the K Yeah, the k invariance is monotonically decreasing at late time. So k invariance is defined as f of e minus f of e tilde. So as we had mentioned, the time at which we see k invariance is a sort of time scale after which all the physics can be said to be captured by random matrix theory. Yeah. So yeah, to summarize these 3 points. So random matrix theory is a powerful tool for studying quantum chaos, characterizes OTOCs, which are used to study early time chaos, and frame potentials, which probe complexity and randomness. And due to hard invariance of the GUE, it can capture the late time physics of a system that has been delocalized. And quantum chaotic systems defined by a local Hamiltonian can be studied before or after the onset of approximate Haar invariance, and that is studied using K invariance. And yeah, there was an interesting question at the end of the paper. So as we have seen, there is some sort of uniform late time behavior in chaotic systems that's captured by random matrix theory. So in that spirit, we can ask, in gravitational systems, is there any late time behavior that can be captured by correlation functions in ADS-CFT? So yeah, that would be an interesting question to consider. Yeah, I think that's the end of the talk. Yeah.
Thank you so much, Soham, for the great talk. Do you guys have any questions? There were plenty of questions during the talk, but if there are any more questions.
I have a question. So this is a basic question. How do you define the probability distribution for random matrix theory? I think you mentioned it at the very
Oh, yeah.
beginning of your
So
talk.
specifically for the GUE, the probability of a certain Hamiltonian is, it goes as e to the minus trace of h squared. In other ensembles, it might be different.
Okay. How do you define the ensemble?
The ensemble is defined as a collection of a certain Hamiltonians and the probability with which it can occur.
Okay, I see.
Sorry, did you mean something else?
No, I mean that way. Well, is there any criteria to choose to pick a certain ensemble for your interest? Like for this physical system, I'm gonna use this
Okay, I see.
ensemble.
So, I mean, are you asking why we are studying GUEs?
Could be.
Yeah. Uh, so that's because, I mean, hard invariance of GUEs makes calculations easier. That
Okay.
might not be the case in other ensembles. That's it really.
Okay, thank you. Also, if I can ask, did this paper, I actually didn't read this paper, but did this paper mention any relation to box scattering?
No, it didn't.
Okay, thank you.
Any other questions? If not, thanks so much, Soham, for the great talk, and I'll if you don't mind, I'll upload it on our Journal Club YouTube channel. Thank you. Thanks, everyone. Have a great day.
Thank you very much.
Thank you, Soham.